tape. So we're done with the all types of problem in the linear expansion. For example, length of pendulum. For example, the error in the measuring tape. Okay, and what else? Yeah, you can also use the moment of inertia problem. So for any object which is made of metal, let's say if you turn about the axis, length is L, and coefficient of linear expansion is alpha. So in such case, the moment of inertia will be proportional to L square, because I'm not trying to specify the axis. You can choose any axis, but no matter which axis you choose, the dependency will be ml square, right? Am I audible, guys?
Yes, sir.
So I, we can attach some constant into L square, and therefore the fractional change in I, di by I, will be twice of dl by. And dl by L we can attach alpha d theta. Yes.
So what are we trying to do over here?
Change of moment of inertia with temperature. Okay. And these things are big issue actually. So let's say if you have an iron gate of this much, let's say big length, which is well supported by the hinges, during extreme summer, if you don't leave a gap between the wall, so it's a very common problem that in the afternoon the gate gets locked actually. Because of the expansion, it will push the wall and will get, I mean, will touch the wall, and therefore it is difficult to open and close. So you might not have faced this issue, but even I have faced this issue a lot in summer in my hometown, because the gate is so large that expansion is significant. So the moment of inertia to rotate will also change, right? You can think this way. So now if you try to open the gate after expansion, the I will increase. So the question is how much I will change with respect to temperature. So what we need to do is we just need to write a relationship with the length, the dimension, and then we can do. So delta will be how much? 2 alpha changing temperature. I think you haven't realized that anything which is having a dimension and which can expand will expand, and anything which depends on that dimension will get affected by the change of temperature. Simple. Understood?
Yes,
Yes.
sir.
Anything, like you can think of any object. If something can
Sir,
expand, and if yes,
sir, so the effect is like in heat, it will, the door will open more or something.
no, it will be more difficult to open the door because I will increase. Na? If temperature will grow, delta theta is positive, delta is positive. So positive means it is increasing, right?
Yes, understood.
So it will be more difficult to open. And you may get question, a very tough question in which the temperature relation and the other relations will be related. So when you will study the chapter of Faraday's law, the last chapter of 12th. So in the Faraday's law, we have the a rod moving in a magnetic field induces EMF, and the induced EMF we write as half B omega L square, which is the length of the rotating rod in a transverse field. And now if the temperature will be brought into picture, the induced EMF will also change temperature because B will not change, omega will not change. Omega will change also. But let's say omega is constant. Then this becomes DL by. So now I can also find the what time? So 2L into DL by d theta, the differentiation. And now we can say that the induced EMF will be a function of temperature. And alpha is the linear expansion, so alpha. So B omega L square alpha into d theta, or you can say dt, not to get confused with angle and all. So if I ask you d by dt, you can write as B omega L square alpha d theta by dt, which means the rate of change of temperature with time, and the induced EMF will have a relation. So the things like this can be created in a questions, like any question where dependency is on temperature, I can link with the expansion chapter. That's the whole idea. So try to understand that where we can apply this concept anywhere. So any scenario. So let's say if you have studied in the so let's say we have a two fixed support and there is a string oscillating. So the string is vibrating. So tension nesting is let's call T. So how we write the tension nesting? Let's say T equals to, I mean, sorry, you write the, okay, we can do like this. If I'm trying to create a question, I don't know whether I will be. So this length is constant. Okay. Now as temperature will increase, let's say the overall length is L. Okay. This length is L, the net length is L. L is the total length. So we define the mu as mass per unit length. Now as temperature will change, then mu will be affected because mu depends on length, and if length will change, mu will change. So we can say uh,
So the small m is the mass of string.
m is the mass of the entire string, L is the total length of the string.
So then that load m down.
Yes, mg, this will become mg. Oh, this is okay, okay. Yeah. So capital M will decide the tension force. That's mg only. So now what we need to realize that we can write mu into L equals to m. M is the mass of the string will not change with temperature. So we can write a d mu by mu plus dl by L is 0 if we differentiate this equation. Okay. And therefore, the d mu by mu and this dl value we can write as alpha d temperature, right? dt. So now you can see that d mu by mu is how much? And of course, as temperature will increase, length will increase, mu will decrease. That's why the negative sign. Do you realize this? Now, velocity of sound is, velocity of wave in the string is under root t by mu.
Yes, sir.
So now this is like challenging for them. This is challenging for many because they don't realize the simple relation. So now because v is t by mu, t is the constant quantity because there's mg, but mu is a variable because of temperature. So I can write as v square equals to t by mu. So mu into v square equals to t, and this t is like basically force. That's why this is a constant quantity. So if I differentiate now fractional differentiation, so d mu by mu plus 2 or twice of dv by v is 0. But we just realized that d mu by mu is minus alpha dt. So you can see twice dv by v equals to alpha dt. So the fractional change in velocity is how much? So change in speed will be the initial speed and this relation. Yes. Understood. So they may give you alpha, they may give you v initial velocity, or you can find initial velocity from the tuning fork and all. So many things we can design this way. Understood. So you think of any concept in physics which you have learned so far in which length is involved. Okay. Think of anything in which length is involved. Then thermal expansion will come into picture. So what I'm showing you is the extreme case. Like these are some extreme situation in which you have to think this way. So dependency should be think about. Like, you have to think about the dependencies of dimension and temperature relation, and be ready for the differentiation and arriving at the answer. I hope this is okay, clear. Anyone having any doubt?
Yes.
So the next concept is from the chapter of elasticity called thermal stress. So thermal stress is developed in an object when you deform it, right? Like stress is developed in an object when you deform it, isn't it? So I hope you have seen the Victoria. You know what is Victoria? It's a horse ride. If you go to Gateway of India, you must have seen the horse ride, right? Am I audible?
Yes, sir.
Okay, if I'm audible, then you can reply. That's how we interact, right? So if you want to make a wheel and generally the wheels are made from the it's wooden wheel mostly in the Victoria. So what they do is after making the wheel, because the wood will not be very strong to sustain the hardness of road. So the wheel is covered with a iron ring. Okay. So what they do is,
Say outskirts.
yeah, so what they do is they make their wheel slightly. I mean, you can say the ring will be slightly is smaller than the wheel size. Okay. So what they do is they heat the iron ring so that it will expand. And in the red hot condition, when it is like expanded, so with temperature, the wheel expands, and you can see that it will capture the wheel, right? Eventually. And what they do next is they pour the water. And once you pour the water, temperature will cool down, and then it will hold the entire wheel very strongly and firmly. So this simple trick is used in the bullock cart, horse cart, or any cart like in which we use the wheel. And it's a very old tradition. Now, still in Britain, as a cultural heritage, they create the wheel and they go to this. It goes through the same process. So what you do is you try to first expand the iron ring in the red hot condition, which is like roughly 800 degrees Celsius temperature, or even let's say 600 degrees Celsius temperature, and then due to expansion, you can fit the wheel inside, and then you cool down. It will become attached to the ring without any fault. Okay. Now that's very interesting. Once you do that, uh, we know that we cannot attain the temperature of 600 degrees Celsius on road, or even the friction cannot generate that temperature, and therefore the wheel will remain attached to the. So after wear and
Ring.
tear, yeah, and after wear and tear, after long usage, sometimes it gets detached also, because the ring is not made of a single iron; it is also hooked together at one end. So sometimes that ends breaks open and it comes out. But the whole idea is thermal stress is a very useful concept. And when we design the bridges, especially the iron bridges or any bridge which you have seen which is made of metal, so they use the thermal stress concept to the weld two objects. Okay. So maybe the two rails are welded together using the same concept of thermal stress. So how we use it to demonstrate that? So first we will see the simple cases. So let's say this is the left end of a bridge and this is the right end of the bridge. And of course these are fixed. And this may be attached to something further. So what we do generally, we bring a iron rod or any rod, and you can see we leave a gap. So the natural length of the rod is L. Alpha is the thermal expansion coefficient. Y is the Young's modulus. A is the area of cross section. So what will happen? Like once you raise the temperature, it will fill the gap in the red hot condition. And after filling the gap, because it's a red hot condition, it will also glue to the metallic wall. So it's a wall of also iron. Or you can say you weld together. So you do the welding. Let's say you do the weld. So first you let it expand and you weld it together. But that happened at a very high temperature. So again, once you try to cool it down, what will happen? The rod will
So it
try
will
to
again
shrink.
contract.
Yeah, it will try to contract because now it's welded together. It will not be able to go there. So it will try to go back, but it is now welded, and therefore it is in a state of deformation because it is not in its natural length. What is natural length? For every temperature, there is one length which is called natural length. The gap will be filled at high temperature. So for that high temperature, that was the natural length, the gap plus the length of rod. But when you go back to the same temperature, then the natural length should be the L only. So gap will behave as the amount of deformation in the rod. Do you realize this?
Yes, sir.
So in thermal expansion, we define dl by L equals to alpha d theta. But this is for free expansion, right? So we allowed the free expansion in the beginning to, merge the gap. But now I'm not allowing it to go back. So the deformation, or you can say delta L, or you can also write as, that's also free. You can always write in this fashion, things like this.
So the same phenomenon happens in soldering iron also.
Yeah. So delta
So
L
and
is called deformation.
so for
Yes.
600 degrees Celsius, that red hot iron will have its natural length at 600 degrees Celsius, and then uh,
When you cool down, the length will change, the natural length will change. So if
yeah,
you cool down, it will try to go back to here again. So at the previous temperature, this is the length, and this length is at high temperature. So when you cool down, it will try to go back to the original length, right? But because it is welded together with the other wall, it won't be able to go back. Do you realize this?
yes,
Yes, sir.
So this will act as a deformation. This is delta L. And luckily in this case, delta L is same as the actual expansion. Because we allowed the expansion of this value and then we prevented the compression, so that becomes the deformation by default. You need to realize this fact, what I'm saying. The expansion becomes deformation. Do you realize this? Yes or no?
yes, sir. Understood.
And if that is the case, then the deformation is dl, which is alpha L d theta, right? Or let's say delta temperature, just like this. So from the definition of stress, stress is defined as Young's modulus into strain. So here we have normal stress and we have longitudinal strain. And the wall will exert a force of F. Area of the cross section we have taken as A. And strain is defined as deformation length upon original length. So original length we can call it. So first write the formula, then substitute the value. F delta L is how much? And L we take as the previous length, smaller one. And this L cancels out. So what we get? So the force developed between the wall and the rod is this much. And that is how the two walls are welded together with a long distance rod. So this stress is sometimes required in designing various structures, because if you don't do that, then it will create more deformation. So first we expand and then we shrink it, and therefore any weight is under stress. So if temperature will rise, then it will try to expand and will release the tension. So this is a simple concept of thermal stress. Like you, what you do is you expand thermally, and then you prevent the compression, and therefore you create the stress. I hope this is clear.
Yes, sir.
So now comes the second scenario. So we have two rigid walls or rigid supports, and now instead of two rods, I mean one rod, we have two rods of equal length. So we are assuming the cross section to be same, and the initial length is also same, but they have different Young's modulus and they have different coefficient of expansion. So now what will happen if I try to increase the temperature? The interface, you can see, will shift either left or right. So question is, as temperature changes, the interface will shift. To find the relation between shift, let's call it x, with delta t. So I think question is clear. Is question clear, guys?
Yes, so
If you want to solve, you can solve. If you don't want to solve, let me know. I will solve.
for 5 minutes, please.
Sir, I'm not getting the answer. Hello?
No problem. So first of all, you need to realize or assume actually.
Sir, can you wait 1 minute? I think I'm getting it.
Okay, great. Think about it. I can wait for 4 minutes.
Sir, I got the answer. Hello, sir. Hello, sir. Hello. Hello, sir. Hello.
Okay. So first of all, what we do
Sir, I
is,
got answer.
Sir, is my answer like correct?
yeah, tell me.
Sir, I sent it on the chat.
Chat. Oh. Uh, no, nothing like that. You have to
Sir,
rearrange.
I got the
I want
answer.
alpha. I want X actually, so you can just rearrange. And there are two A1 alpha one, alpha one Y1, alpha two Y2. You have written just only one, so how it would be correct? So many things
Uh,
are missing, right? Anyway.
sir, I got the answer. So X is equal to
Hmm.
L delta T into
Hmm.
alpha 1 plus alpha 2.
No. So first of all, you need to realize a lot of things. That first of all, let's say I'm assuming the shift towards right. Let's say the yellow one is more powerful in terms of thermal expansion. If the shift I will assume as X, so naturally, if you increase the temperature, the natural expansion of the first will be how much? the delta is small l will be how much? L alpha 1 delta t, right?
Yes, sir.
But this is, it is trying to expand, but how much you are allowing to expand actually? Only x, correct?
So can we say that the like x will be the expansion minus the stress in it?
Yeah, so deformation of the first rod will be the expansion minus x. Understood? The first rod is getting deformed by how much value? You're not letting it go as much as it wants. So it wants to go to this length. You're allowing only x value. So rest is called deformation. Do you realize this? What I'm saying?
Sir, I by mistakenly added both the values. I wrote delta L1 plus delta L is equal to x.
Just a minute. Now coming back to the thermal expansion of the second rod. Yes. It can expand by value L alpha to delta t. Correct? The free
Yes, sir.
expansion thing. This is a free. This is a free expansion. But not only you prevented the expansion, you compressed it further. So the delta L2 is how much? Tell me. So the blue will try to go this way, no? And the yellow will try to go this way, correct?
Yeah.
So how much deformation has occurred in the blue part? You can see it's this much.
Delta L2 plus x.
Correct. So the delta L2 is x plus the deformation part, like sorry, expansion part. Now, when I say equilibrium, it means the force by which the orange will push the blue and vice versa must be equal. So for equilibrium, the F1 must equal to F2. And now we have to go back to the definition of stress. So force upon area is Young's modulus into strain, which is delta L1 by, we'll keep it L, the initial. And therefore we can also write a F2 by area equals to, and now you can equate it, right? So if you solve from now, you can get that. So can you please solve this part now? Like manipulate and tell me the final answer for x. Can you guys do it now? Or you can do this also. So
So
AY1,
F1 and F2 will be in the answer.
pardon?
So F1 and F2 will be in the answer.
No, you have to equate it, no? So we are equating the force, no? So we are getting the force from these two equations. These are the equations in which you can get the force. Use these equation to substitute here, and this will give you this relation. So the equation is y1 deformation first is, so y1 into delta L1 is delta L1 minus x. This is x plus delta. So y1 delta L1 minus y2 delta L2 is x into y1 plus y. So, and delta L1 is how much? L alpha. Okay, so I can take alpha. So what will be the condition for no shift? For no shift condition, we must write y1 alpha 1 equals to y2 alpha. It's a very famous question, and you may face in various competitions. So you need to realize the meaning of thermal expansion. you need to realize the concept of natural length or true length of an object, and the length of the object is defined at a given temperature. So there is nothing like a absolute natural length. So the free expansion will give you the natural length, and whenever you will prevent the free expansion, what will happen? So whenever you prevent the free expansion, stress will develop.
Oh, yeah, sir.
So that is why in case of railway tracks, the gap is left after some length. Because if you don't really keep the gap due to the thermal expansion, it will try to develop stress, and the stress may lead to the deformation also. So here we are preventing the distortion in the shape. So we are assuming that the distortion is not happening, but in the real life, the stress will eventually lead to the distortion, and the trains will derail. So that's why when you see the railway tracks, after a few meters, they leave a gap because expansion can happen. Understood?
Yes, sir.
Okay.
So if there was free expansion, if there the two block parts are not there in both the side, then we have to just add first and the second
Pardon?
equation, and we'll get it.
Once again, tell me
Sir,
again.
if we remove both the side,
Uh, yeah, so if you remove
yeah,
both
if we
the
remove both
wall,
the
it
side,
will, yeah, they will expand freely only. They will go left and right.
So there will be nobody to oppose the motion.
No, no, no. Nothing will oppose. They will expand.
so we have to simply add both equation, no?
Yeah,
Like,
yeah, correct. So in that case, no force will develop. Like there is no need to write any equation of equilibrium, right?
yes,
The
understood.
equilibrium is not required in that case.
Sir, but won't they both oppose each other in the center?
No, no. I mean, see, they are getting at least one end to expand. Na? So they will start moving towards the other end, because a slightest force, see, if there is no friction between the surface, a slightest force will push you back.
Yeah.
And also, if friction is there, in that case also, it will stop the other end to move. The other end will expand. What's the problem?
Yes, sir. Understood.
There is a very challenging problem. It's Olympiad level and beyond that problem, which I would like to visit because I haven't solved this before. So give me 2 minutes. Pull out my book. This question is only for myself. Don't worry. This is the right time I should. The problem is, Hmm. The next question is called bimetallic strip. You can also make it trimetallic or n-metallic. Am I audible, guys? Hello, hello, hello. Am I audible? Atharv and Harshit. Hello, hello, hello. Am I audible?
Yes, so you're audible.
So question is, the bimetallic strips are very useful object, and generally these are employed in creating the auto cutoff system. So if you have a geyser at home, after certain temperature, the geyser gets cut off. So it will automatically break the circuit and prevent the further heating process.
Yes, sir.
The same is with the iron with knobs. You might must have seen that iron will have the various type like silk, linen, cotton, and you can have the various mode in which you can put the knob and you can press uh, the required cloth. So how we maintain that? Okay, this cloth must be pressed at this knob. So these knobs are these modes are created using the bimetallic strip, and the purpose of bimetallic strip is to create a circuit breaker. So how they do it? So we take two thin strips. It is very thin, few millimeter thick. So in reality, they are very thin, few millimeters. I think less than that. So if I draw something like this, I won't be able to explain. So I will zoom it. Oh, this is a new feature I discovered. Oh, cool. I never thought about this is a feature. Ah, this is amazing. I just discovered the new feature of Zoom. Oh, cool. So if I draw anything and if I click, okay, this is the text part. Design. Ah, okay. Just a bit, guys. I'm just thinking how to use this later on. So let's say I want to click here. Yeah. So any box, if I click, it will become a text of that size. Then I can choose the font size. Then I can write. So yeah. Okay, nice.
Sir, but then that box will stay white only, the text box.
No, no, the text box will not hide. See, if I write anything, it's there.
Oh,
That's interesting. No? So I can actually put some annotation in the diagram also. Okay. So generally, there is a method called a text which I can use, but this is something which I just discovered. Uh, but anyway, so in case of bimetallic strip, what we do? So you take two thin rods, simply thin strips. Let me change the color. And these two are glued together. So it means uh, so now if the thickness of the each strip I take as T, and if I call the length as L, T is called thickness. So when you glue them together, and if the thermal coefficient of each rod is different, and if you assume that alpha 2 is more than alpha 1, so the orange will tend to expand more than the pink one. So once you raise the temperature, what will happen? How to make sure that one expands more than other? So alpha 2 will expand more than alpha 1. In that case, is only possible when it will bend like this. And because alpha 2 is bigger, so the outer rod will be here. So you can see clearly that upon hitting, the bimetallic strip will bend. Now, what we do is, so in a circuit, we use a bimetallic strip as a connection. And let's say this is alpha 2 and this is alpha 1. Think about this situation, alpha 2 is more than, and this end is like fixed. And then we have the continuing circuit. So as the current will flow, it will create the heat in this part because the bimetallic strip will have uh, some sort of resistance. And due to the heating of the strip, it will try to expand. But upon expansion, because this end is fixed, it will turn this. Do you realize it will turn like this? Because alpha 2 is more than alpha 1, alpha 2 is more than alpha 1. It will turn upward and it will break the circuit.
yes, sir. Understood.
And once you break the circuit, then current will stop. So it will take some time to come down. So it will cool down and then it will come back to the circuit and it will again establish the current. So that is how we create the auto cutoff. The moment temperature falls down, it will come back. So we choose various combination of metal and alloys, not just metal, which are having the sufficient bending at a given temperature. So that is how we establish that the silk must be heated to this temperature, and therefore this combination of bimetallic steel will work properly. And that is how, by taking the proper pair of bimetallic steel, we can create a different pair, different temperature sensitivity. So they develop this temperature sensitivity, and that is how they make sure that only these temperatures can be attained. So in the iron knob, when you have multiple modes, which you might have seen, like silk, linen, woolen, and cotton, and something more also. Those like below that knob, what we have is a pair of bimetallic strip for every mode, and they only what they do is they act as a make or break circuit. Okay, so that is how this works. I hope the concept is clear how it works. So the one with greater expansion will bend all right. So it's the biometric strip I have make it smaller. That's not an issue. And once it bend, it will have some curvature, some radius. Mm, mm. Okay, so what we call is a radius of curvature. So it will bend and it will have some. So we take the mean radius as a radius from interface, not from the other place. So the radius of curvature of this bimetallic strip will be from here to the mean radius of the bimetallic strip, and the length of each strip will be their mean length, which means their center. So this is how we take the length measurement of curved object. So the length of the first object or the first rod, let's call it L1. What is the natural length that we have to take here? Not the, so the length of the first object is how much in terms of R? Because the thickness is T, so this will be how much? R minus T by 2. I hope you are
So
getting
R minus 2.
R minus T by 2 into T into alpha. This one. So the length we can write as arc length. No? This is the arc length.
Ah, yes, yes.
So we can write as R minus T by 2 into alpha. Alpha is the angle of the arc. And similarly, L2 will be how much? And you can clearly see that these are the final lengths after the temperature is raised. The initial length is how much? L. So can we write L1 equals to L1 plus alpha 1 delta theta and L2 equals to, so do you realize this part first of all?
Yes.
Okay. So T is very small. So T is very, very small than R. So this approximation will help you. And therefore, the ratio of the length and the R ratio we can find easily. So L1 by L2 we can write as, or let's write it L2 by L1. That's bigger. So L2 by L1 is how much? 1 plus alpha 2 delta theta upon, correct? And if you remember this, we can write as 1 plus alpha 2 minus alpha 1 into delta. Now, if I write the ratio from the above two relation, this is from 3 and 4. And 1 and 2 implies okay. So this we can write like this.
So T is very small than R. Right? Then we can
Pardon?
ignore the T. T is very small than R, so we can ignore the T.
Yeah. So again, we can use the simple approximation, and this is, we can write as 1 plus T by R minus T by 2, which is same as uh, 1 plus T by R. We can write like this. So now we have the equation 5 and 6. So from 5 and 6 we can write it 1 plus alpha 2 minus alpha 1 into change of temperature is 1 plus T by R. 1 cancels out, right? So this gives us radius of curvature is how much? T upon the difference of temperature into, and this R is very large because the alpha 2 and alpha 1 we don't keep it simple like difference is very small, so the R is actually very large, and that is why the bending is by few degrees, and the thickness will decide the bending. So by keeping it really thin, the bending is very small. And why we do not want a lot of bending? Because the space within the box in which we try to design is very small. So we want to break the circuit by small changes. Okay, so slightest change will be able to break. And why we are using the approximation? Because R is so large that these approximations are well valid. So that is how we solve the question of bimetallic state. Is this clear? Okay, so we'll not solve for the trimetallic, but we'll see something more about it. So this is the case when bending is oh no. Okay. So now the next question is concept is so imagine we have a confinement and okay, let's make it 3 rod right. So what we have is alpha y so that means plus y a and alpha. Okay, so we have these relations which doesn't look nicely. Y1, A is same, L is same, Y2, okay, Y. Just experiment. Okay, let's remove this. This is of no use. Okay, anyway. So what we have is the first rod is Y1, alpha 1, area is A, length is A, Y2, so let's do it for the time. What we do is we prevent the bending by putting something above and below. So it's a rigid support. So I'm preventing the bending. The only way they can move is horizontally. Okay. So the question is if I fix the other end, this end. Yes. So upon expansion, depending on their ability of expansion, alpha 1, alpha 2, alpha 3, the first may try to go up to here, The second may try to go up to here. The third may try to go up to here. I don't know. I'm just taking it randomly. But will they able to go to that length separately? If they are free, they can take. But what if they are glued together? What if they are like acting as a trimetallic strip? So they will settle on somewhere here, right? Somewhere here. And if they will settle on somewhere here, it means the stress develop in the bottom two will be left, and the stress develop in the top will be right. And then you will balance the force that F1 equals to F2 plus F3. Okay. If I choose this rod here, that's not possible. Then it will expand everyone and all will try to pull back. And therefore, I can say that the sum of all force must be 0 for equilibrium. And why I choose this particular way? Because mathematically it really doesn't matter. And this way of assumption, we can tell you that what is the deformation in each rod. So how much you are deforming the first rod? Can you guess? So if I call the displacement of the common interface as x, what is the delta L1? Can you guess? What is the deformation in the first rod? See, the dotted lines are representing the natural expansion, the thermal expansion. So how much we have deformed each strips individually. Tell me. The first rod will deform by x minus their natural expansion, because that is I'm allowing. So this is the extra.
Yeah, sir, I didn't know what to say for the natural expansion.
Yeah, so you can you can call it some value. So this is x minus okay. So delta L1 is how much? Alpha L delta theta, right? We know this answer. So these are the relation of free expansion, right? We are not restricting at all, right? Then this is the possibility. But here you can see that everyone will deform like this, and therefore the force upon area equals to Young's modulus into strain. You can add force equals to Ay delta L by L. Now apply this formula to the equation in this equation. So what we can write is, since the sum of force must be 0 at equilibrium, F1 I can write as A by L, we can take common. Y1 delta L1, Y2 delta L2, Y3 delta L3, and A by L will become 0 only. So delta L1 is how much?
Alpha 1 and delta theta.
And this way of derivation you can do it for the tetrametallic strip or a pentametallic strip, and doesn't matter. So no need to worry about which one will expand more or less. I mean, just think x as bigger than all three, and then solve it. So what you can get is something really nice. So answer is y1 delta L1, the free expansion, y2 delta L2, y3 delta L3. And if I substitute the L1, L2, L3 relation, you can see clearly the answer will be y1 alpha 1, y2 alpha 2, y3 alpha 3 upon y1 y2 y3 whole into L delta t. Okay. So for any metric is to be connected as x equals to summation of yi alpha I upon summation of yi. Yes, upon. Okay. So these are questions from SC Verma. Thermal chapter, of course, expansion chapter. You can get these questions, and we are done with the linear part. I think complete. Now nothing is left in the linear expansion at all. So we have seen almost all varieties of questions. Yeah. Okay. So now we can go to the next concept. And that is the second part called superficial expansion. So we know that expansion always occurs at atomic scale. So we know that two atoms will go away from each other. So if the atoms are arranged in a two-dimensional space, then the linear separation of each atom will eventually lead to the change of area. And such expansion we call it superficial expansion. So let's say if we have uh, a metallic plate, so upon heating, it may become like this. So if I call the length as L and width as let's look at X and Y. If I call length as X and width as Y, you can see later on after expansion, length becomes X dash and Y dash. So I can also say X is X plus dx or delta X and Y is Y plus delta Y. Correct. So what is the old area? The old area we can write as A naught, that is X into Y. Okay. And so what is the new area? Let's call it A theta, which is X dash into Y dash. So A theta upon A naught will be how much? So A theta by A naught will be X dash Y dash upon XY. And now you can write as X plus delta X into Y plus delta Y upon okay, anyway, then you can write the way you know. Or the way of other way of writing is we can use the concept of thermal expansion. So we can say so now it is not necessary that the property to expand along X and the property to expand along Y are same because of the different crystal structure. The expansion may occur at a different differently. So we call the expansion coefficient along X as alpha X and expansion coefficient alpha Y as alpha Y. So if we choose two different coefficient of expansion in two different direction, because now generally in lattice this kind of phenomena happens. This is called what do you call an isotropic an isotropic medium, right? So what is isotropic? Iso means
When
same,
all
tropic means
sides
direction.
react the same way.
Yeah, if the property is same in all directions, we call isotropic. But if the property is different in different direction, what we call anisotropic.
And isotropic.
So this concept is very, very important. So in fact, you can add x dash equals to the old length into 1 plus alpha x delta theta, and you can say y dash equals to understood. So if you substitute here, what you get is so the a theta becomes how much? So you just need to expand. You get 1 plus alpha x plus alpha y into delta theta plus the product term alpha x. So what we do is this term we can equate to 0 because it's a product of 2 alpha. And so the answer becomes the area at a given temperature is initial area into 1 plus the sum of the alphas in different direction uh, into delta theta. That's the answer. So we prefer to call this term as beta. So let beta, which is the temperature coefficient of superficial expansion, temperature coefficient of so if this is the temperature coefficient of superficial expansion, then the a theta we can call it a naught 1 plus beta delta theta. And what you can remember, what you must remember, in fact, where beta is alpha x plus alpha y. That's a formula. Okay. So now, if you call the medium as isotropic, things will change, right? So for isotropic medium, the alpha x will be same as alpha y, which we can call it alpha. And in that case, beta becomes 2 alpha. Understood? So for isotropic medium, you can replace beta in terms of 2 alpha. And that is why, in case of metallic sheets or metallic rod or metallic even volume, cylinder, metallic anything, in case of metal, they don't give beta and gamma. They only give alpha because they know that you can derive beta from the alpha, you can derive gamma from the alpha. And for isotropic medium, every coefficient we can relate with alpha. Understood? So you will see this very common in numericals that they don't give beta and gamma. They simply give this. If you want to write in the differential form, again the equations for isotropic medium, you can directly write the result. You can see the fractional change in area. You can say beta equals to dA by A upon d theta. It's like what is the fractional change in area per unit change in temperature? It is 1 by A into dA by d theta, and you can again do the same old method or trick. So these formulas are only for isotropic medium. That's why in the beginning I didn't give you the formula here because it depends on the assumption of isotropy. If it is not isotropic, then we have to expand only along one direction using the linear equation or linear expansion, you can say. So that's why I cannot write something like this in the beginning. So for isotropic medium, you can write like this, and then if you want to integrate, you can integrate. If you want to do something, you can do something. So A naught to A theta, 0 to theta, and if again if you take beta as constant, so if beta if we take as constant, then the ln A by A theta by A naught is beta theta, and then you can say A theta equals to A naught beta theta, and then you can expand and so on and so on. And all this term will be high power beta, we can take it 0, and then you can equate it. The very old form. Okay. Now, generally, from the superficial expansion, nothing much will be asked to you. So what they'll ask you simple question like, if you have a metallic plate and if you have a hole, so radius of the hole is A, and distance between these two centers. Okay, let me make it square so that I can have less. Okay, enriching this. Okay. So let's say the side length is B, this is A, this is the gap is C, and this length is so upon heating, which dimension will increase and which will decrease? Tell me. A, B, C, W, L. So following this dimension A, B, C, W, L, which one will increase and which one will decrease?
Sir, L and W will increase.
A and W will increase, right? And what about A, B, C?
So B and C will increase.
Pardon?
B and C will increase.
B and C will increase. Once again, tell me.
B and C will increase.
Okay. And A?
So can you tell the answer for these?
Yes, tell me.
So can you tell the answer for BC?
See, if you heat something, everything will expand. Nothing happens. So A, B, C, L, W, all increases. Simple fact. And to demonstrate the same, let's say, if you think of the atom near the perimeter of this circle, if you think of the atom near the perimeter of this removed part, the square, expansion does the atomic changes, which reflects on a big screen. So all dimension must increase, right? The separation between the atom increase. So imagine if the periphery atom will increase their separation, the gap will become bigger or smaller.
Bigger.
Bigger. So everything will expand. So even the hole will expand. So whether we have
Sir, everything
something,
will expand.
yeah, everything will expand. So if we have a hole, upon hitting, even the hole will expand within the metallic sheet. So nothing decreases, everything increases. And upon cooling, everything will shrink no matter what, whether it's a hollow space or a full space, a filled portion, it will expand. So now if I ask you that if there is a, if I give you a ring, this is like very counterintuitive. And if I say upon hitting, the gap will,
Increase.
upon hitting, D increases. That's simple. Like if you're hitting something, everything increases. It will become a bigger gap and bigger ring also. All right. So the whole idea is the shape remains maintained. And if you think in terms of shape, this is the center, so it will become eventually a bigger circle. And the gap will maintain the angle. You can think this way also. So from the superficial explanation, what they will ask you, the simple relation like this, and then we have the actual question coming from the. So we have something called volumetric expansion, and also this is called real expansion. So in case of volumetric expansion, or we call it a real expansion. Okay, so if you have a solid object, so if you have a three-dimensional object, which I need to draw. So volumetric expansion of the solid object is quite different from the liquids and gases. So upon heating, even if you start with a cube or cuboid, let's call it cuboid. Upon heating, all dimensions will change differently if it is n isotropic. So if I call the ability to expand this way as alpha x, ability to expand this way as alpha y, and ability to expand this way as alpha z, then the V initial, if you call x, y, z, then V final will be called X dash Y dash Z dash, correct? Where X dash will be X into 1 plus alpha X theta. In every dimension, you can write the linear expansion concept. Y dash will be Y into 1 plus alpha Y theta. So we always start with the an isotropic case. In case of liquid, we don't have such scenario. In liquids are always isotropic. So in liquid, the properties are not different in different direction. This n isotropy is the property of mostly solids. So you can also write the z dash equals to. So the x dash, y dash, and z dash is equals to how much? Okay, the new volume is, and this we can write as x y z into 1 plus alpha x theta. So now you know how to expand this. You can write as this as v naught, and this is really big term. So you have for 8 terms in total. So what we do is we only take the first power. So 1 will be 1. And the other term which I would like to take is the 1 into alpha x, 1 into alpha y, and this will give us. So we have taken the 4 terms, and the rest of the 4 terms will be x, y. I cannot like this, all terms x, y, y, z, z, x, and the 4th term will be alpha x, alpha y, alpha z, theta q. So if you really want to expand, you will get something like this. And anything more than linear will be 0 in our calculation. And that is why the volume at any temperature theta is equal to volume at 0 degree. And what we get is 1 plus. So we write gamma as, and this is called thermal coefficient of real expansion or volume expansion or volumetric expansion thermal. So gamma we got as this alpha x, okay. And therefore the volume at theta we can write as P naught. So for now you can actually correlate the isotropic case, which is very common. So in solids we may have the n isotropy, but in case of liquids it is almost, I mean, it is always isotropic. And so we can say that for isotropic medium, gamma will be alpha x plus alpha y plus. Alpha x will be same as alpha y will be same as alpha z, and let's call it alpha. So gamma becomes thrice of it, right? So gamma of solid we can write as thrice of alpha. Generally, alpha is given for solids, right? For liquid, we always assume isotropy, and therefore gamma of liquid is, we just call it gamma. We don't call alpha because alpha we cannot define for liquids. Okay. So in case of liquid, we only define gamma. So liquid will have gamma 1. The solid will have alpha, and the sheets are of course solid, so we can't have liquid sheets. So for isotropic medium, for isotropic medium, alpha, beta, and gamma are related. So we have seen beta is 2 alpha, gamma is 3 alpha. So we can write it from here. Alpha is beta by 2, and alpha is, so we can write as alpha equals to beta by 2 equals to gamma by 3. So for isotropic medium, this is the scenario. Alpha is beta by 2 equals to gamma by 3. Is this clear?
Yes.
Okay. Now the formula for the expansion is same for a solid as well as hollow objects. So for example, in this case, the expansion formula for the empty space will follow the same formula as if it is filled. So the expansion doesn't matter whether we have the hollow object or solid object. So let's say if you have a glass of, if you have a metallic glass, a glass tumbler. So if I consider the volume, this volume, then I must apply the volumetric expansion because this area will expand and this length will expand, and so the volume will expand. And because it's made of same material, so when the material is same throughout, the shape will be undisturbed. So things will grow in proportion, and therefore you can apply the volumetric expansion. When you cannot apply, if we have the upper portion made of some material and the base is made of some other material, in that case we have to do the separate expansion and then calculate the volume eventually. So as long as you're solving problem in which everything is made of single material, then even it is hollow, don't worry, you can think as a solid and think of the expansion, volumetric expansion formula, and you can apply it. Okay. So keep this in mind, just in case you get confused at times. So generally in this chapter, what we study is the container and the liquid form. Like this is called the apparent rise and fall of liquid in container. So if we have a container, so if the base radiuses are height as h, of course you can write volume as pi r square. Okay, but we are not interested in those things. What I'm saying is, if it is filled with what? So the water height we can take as some value. So let's say the volume of liquid inside is VL, and the volume of container we call VC. The container is made of solid, so gamma of container we write as thrice alpha. Generally, they will give you the alpha of container. They don't give gamma directly, but you can find. And gamma of liquid they will give you as gamma L. Okay. Thermal coefficient of what? Volumetric expansion of liquid. So you can understand things like this. So what happens? Let's say if the change in volume of water is more than the change in volume of the, because when you heat, both will expand. Understood? If the container expands much more than the liquid, what will happen? Apparently, it will fall. Understood? So imagine the container is increasing by some volume, and the liquid is expanding by less than that volume. So with respect to container, the liquid will fall. That's called the apparent rise and fall. Understood? So what will be the condition for the apparent rise? It's very simple. For apparent rise, which one should expand more, container or liquid? So the volumetric expansion of the liquid should be more than that of the container. And we know the formula for delta V. So delta V by V is gamma delta theta. That's simple relation. So if you substitute, what happens? Delta V liquid is V liquid into gamma liquid into delta theta, and this will be more than V container gamma container this, and because that this will cancel out. So volume relation and the gamma relation is sufficient. So you can write this also. This is called the condition for apparent rise. For apparent fall, the VL gamma L just reverse the inequality. That's it. And for no apparent change, so for no apparent change, what we can write? The length as this relation must be equal, which means the volume ratio, the fraction of volume that you must fill is the fraction of gamma. And this is the no change can only occur if gamma C is less than equals to gamma L. Because if gamma C is more than gamma L, then V liquid becomes more than V container, which is not possible. So it will spill out the water, right? So what will be thrown outside? So imagine Okay, these are cases. Okay, you will get question based on these simple formulas. That's it. So we'll go to the next concept. Imagine if we have a container. Now, if you fill the container, if the volume of container is same as volume of liquid filled, what will happen? If both the volumes are equal, in that case, if you heat the system, both will expand, isn't it?
Yes.
So now there are two possibilities. If container expands more than the liquid will be inside the container. It will be like still preserved. But if you increase the, okay, if the gamma of the liquid exceed the container, if gamma of liquid is more than 3 alpha, which is gamma of container in other way, in that case liquid will expand more and therefore it will spill out. So the volume that will spill out will be how much? So it's very simple. The difference you have to take, right? So we can write as gamma liquid minus gamma container. So delta V will be how much? The V into this into the difference, right? This is the extra spill, isn't it? It is clear.
Yes.
Yes, sir.
So what we are doing is we are trying to find the volume of the liquid, new volume, the change in volume of the liquid and change in volume of container. So the container will try to accommodate some value, but rest will be thrown out. And this gamma L minus gamma container is called gamma apparent. So what is gamma apparent? Gamma of liquid with respect to container. And you can use the relative formula like gamma L minus gamma. That's it. So we call it gamma apparent, and these questions will be asked you that apparent is given to find the other relation. Okay. So rest, I hope you can figure it out on your own while solving the numerical, or you can ask a doubts in tutorial. Okay. So now we have the effect of temperature on various properties of liquid. So we can say effect of temperature change on density of liquid. And we know that when you increase the temperature, volume will increase, so density must decrease because mass is constant. So mass we write as density into volume. So in the beginning, we can write as initial density in the initial volume. So we can write like this. And therefore, the rho becomes rho naught V naught by the new volume. And therefore, you can write as, it's very simple, listen, gamma. That's theta. We are comparing with the zero temperature. This is rho equals to rho naught. But don't apply this formula for the water because water will have anomalous expansion. We know from chemistry also. So in water, what happens? So from 0 to 4 degree, temperature will, the density will first increase actually. So whatever is the density at 0, at 4 it will decrease, increase. It becomes maximum at 4 and then it starts decreasing. Okay. And why this happens? Why this happens? Anybody knows?
Motion.
So you must have heard about the H bonding. So at 0 degrees Celsius, every water molecule is bonded to the other water molecule by H bond, which is triple dot. These dots are different. This triple dot is for the H bonding, and therefore there is a gap. So the moment you increase the temperature from 0, the H bond will break and they will come closer, and therefore density will increase. Understood? So what happens? At very low temperature, the H bond is very effective. As temperature will increase, the H bond will be given sufficient energy to be broken into. Okay, they'll break the bond simply, and that will release the water molecule. And because of the bond of breaking, the energy is consumed in bond breakage. So kinetic energy of the H molecules is still less, so they will come close. Now, further, if you give temperature, then they will have more kinetic energy that will let them sit apart, and therefore the density will further decrease. So that's the reason of anomalous expansion of water. I hope you are knowing this anyway. So density will change. So now comes the effect on buoyancy. So buoyancy is all about the difference of temperature, difference of density. So if we have rho is rho d as density of object, and rho L as the density of liquid. And if alpha D is the linear combination and gamma L is the liquid. If gamma L is more than 3 alpha D, what does it mean? The liquid will expand really fast then, the object. And if liquid will expand really fast, it will become lighter, it will become rarer actually. And therefore, the density will fall rapidly. So if density will fall rapidly, then buoyancy force will decrease. Okay, because the object is not expanding as fast as possible. But if the object will expand faster than this, what will happen? If object will expand faster, then the volume of object will increase more than the decrease of density, and therefore the bond force will increase in value. Okay. So you can think that also. And if you want it mathematically, I can write the entire formula. So what you can write? The bond force will write as V rho G. G is constant. We can write as the V1 rho 1 equals to V2. Okay, not bond force will change. Sorry. So let's call it a bond force in the beginning as V rho, and bond force at 0 degree, and bond force at beta degree. So this is the volume of object, because it's completely submerged. Actually, we are assuming it's completely submerged. So I'll draw the diagram first. So this is the liquid, and we have the object somewhere. And therefore, this is the volume of, and this is rho. I hope you are getting the main rho, and bond force is like this. So bond force is how much? V rho G. So now the new bond force will be how much? New volume and new density. So the old bond force upon new bond force equals to how much? V dash rho dash upon V rho. Let's write the formula. The new upon old. V dash is 1 plus gamma gamma density of object, gamma d into theta. I hope you can understand. V will change by this formula, and the rho will change by formula rho upon 1 plus gamma liquid into theta, and then V rho is anyway there, so V rho will cancel out. So this upon this will be 1 plus 3 alpha d theta. This is how we write. So if the term on this part, if this term is bigger than the below part, it will have more buoyancy, and if it is less buoyancy. That's simple relation. Understood?
Yes.
So buoyancy will increase if the object will grow faster than the liquid will grow. That's simple relation you can understand. And yeah, based on this, they may ask you some further questions. Okay, so now let's talk about the gases. So if you have a gas in a moving piston, so if you have a gas expand, I'm like put in this piston, and if you increase the temperature, let's call it delta T or dt, the volume will expand. So I want to know the gamma with. So I'm assuming the isobaric condition. So if P is constant, that's called isobaric condition. Then what will be the gamma of the gas at temperature T? So we have to find the gamma of the gas at temperature T, and we know that gamma of a gas is thermodynamically dependent. So we don't define separately. For gases, the gamma we can derive. How? So I am taking the case of P constant. So we can write PV equals to nRT. So for isobaric condition, P dV equals to nR dt, correct?
Yes.
So P is constant, dV. So that's all right. And what else we can write? We know that what we know. You can divide these two equations. That's what we want. So 2 divided by 1 will give you what? dV by V equals to how much? dt by t? Yeah, that's correct. Now this is the question. And from gamma definition, what is gamma? Volumetric fractional change in volume per unit change in temperature. So by default, gamma is defined as dV by V dt. Understood? Right? That's the definition of gamma. No? Fractional change in volume per unit change in temperature. So dV by V is gamma dt. Okay, don't remember. Okay, we have done this in further explanation. Okay, so you can clearly see that the gamma of the coefficient of volumetric expansion of gas is inverse of temperature. I think you are not realizing that.
Yes, understood.
Understood?
Yes.
Yeah, so now understood.
So at isobaric condition, of you can say at constant pressure, the volumetric expansion coefficient of a gas is actually inversely proportional to temperature, and that's why in gas we can relate these terms easily. So they will ask you for thermodynamic system, define gamma, and here I took the isobaric case. They may take some other case. Okay. So in other case, gamma will change in a different way. So let's try to understand the gamma of other thermodynamic equation. Just I will take one case and I will leave this for the day. That's chapter is over. So for other process, let's say if I talk about
Isothermal.
yeah, isothermic, but isothermic, all right. So it will become dt will be 0, no? So you cannot change the temperature, so you can't have the gamma. It will become infinite. Okay. Okay. Anyway, so we can take some better. Let's take polytropic. That's easy. I don't want to take any risk. So PV power x equals to constant. dP by P plus x dV by V equals to 0. And PV power gamma minus, x minus 1 is again constant. So dt by T plus, yeah, that will be better. You can just use this. So, okay, we got the answer. So we have dV by V dt as minus x minus 1 upon T. So gamma we can define for gas if x is less than 1. Because gamma cannot be negative. If it is negative, it means if you increase the temperature, it will shrink. That's very non-intuitive. So if x is 1 less than 1, it will be positive number. And then gamma gas we can define. And we have various processes. Let's see if I give you PE power 1 by 2 equals to 0. So in this case, you can see clearly, or they may give you a question like this. Let's say in a process, P square V is constant, which is PV half is constant. They'll give you like this. And therefore, you can say X is how much? 1 by 2. And therefore, you can say gamma of such gas will be minus 1 by 2 minus 1 quantity, which is 1 by 2T, right? So questions like this we can create, and We can relate a variety of things in physics, especially in thermodynamics. So try to understand these things, and this completes the thermal expansion chapter. Okay. So rest you can explore. If you have doubt, you can ask. We'll start with some new chapter.
So which chapter?
Pardon?
Which chapter are we going to start?
I am planning for maybe geometrical optics. Okay.
Thank you, sir. Thank you, sir.